Okay, so let's start from where we left off. Let me draw the circuit that we were discussing in the last lecture. We had a circuit like this. I'm going to use slightly different terminology now. I'm going to call this R pi. I'm going to call this GM V pi. Call this RC. Call this the output voltage here. Call this the input voltage here. And alright, so this is the circuit that we had looked at, right? This is the circuit that we had looked at. Everybody, please write down what is V0 by Vs equal to. What is Rin equal to, and what is R0 looked at from here. R0 equal to. From yesterday's discussion, one should be able to write this down very quickly. V0 by Vs is, now you don't have to calculate anything, you should be able to say very quickly V0 by Vs. What is the answer? V0 by Vs is equal to, minus, don't forget the minus sign, minus GMRC, right? Minus GMRC. Okay. What about Rn? Rn is R pi. What about R naught? What about R naught? Looking from here. So we said looking from here is infinite, right? So looking from here would be RC parallel infinite, so it will be equal to RC. Correct? So that's fine. Okay. Alright, let's come back to the next circuit that we were looking at in the last lecture, which was here. Now let me put it here. R pi GM V pi. As usual, this would be V pi for us. Then we put here RC here, we put here V naught again, and we put here a resistor RE. Okay, resistor RE, and we put again Vs. Alright, we put here again Vs. Now, slightly simplified version. So the issue is now, here again, let's write down what is V0 by Vs equal to. What is Rin? Rin is from here, when I look from this side. And what is R0? When I look at from this side. So again, Rin is what? Why is this going? And R0 is equal to what? Okay. This is our circuit number 2. What did we learn yesterday? That this resistor, when we see from this side, what happens to this particular resistor? Multiplied by right, 1 plus GM RPi. So we are saying that when you look at it from this side, this part of the circuit, it appears as if it is RPi when I look at it from here, right? When I look at it from here, it appears as RPi, and this connection between here and here, RE, it becomes a new resistor which is RE into 1 plus GM RPi, right? So that when I look at the circuit from here, RE becomes RE 1 plus GM RPi. So R input is straightforward. R input, when I look from here, Rin is RPi plus this. So that's straightforward. We can write RPi plus RE 1 plus GM RPi. That's straightforward. R0, if we look at it, R0 is also straightforward, because when I look at from here, this is again infinity, and then this is R0, so R0 is RC. Infinity or very large, so R0 is RC. The problem is V0 by Vs. What is that equal to?
Minus GM RPi RC by RPi plus RE times.
Right, so how do we do this? So note that Vs, to calculate V0, we need to calculate V pi. And how do we calculate V pi? This is telling you how to calculate V pi. Right? How to calculate V pi is a voltage divider. So all that we need to do is to calculate V0 by Vs. So V0 by Vs, we can do like this here. V0 by Vs equal to R pi divided by R pi plus RE 1 plus GM R pi. So this is this factor which tells us what is the voltage drop here, then multiplied by minus GM RC. Minus GM RC. Okay. Now note that if we neglect this factor here 1 that you see here, what does this expression simplify to? What does this expression simplify to? Because normally we will find that this GM R pi is a fairly large quantity, much larger than 1. So if we neglect this 1, what does V0 by Vs turn out to be? Are you all seeing that V0 by Vs now? V0 by Vs is equal to minus GM by 1 plus GM RE. So if you go back and look at the previous case, when there was no RE here, the gain of the circuit V0 by Vs was GMRC. When you put a resistor RE, the gain becomes GMRC 1 plus GMRE. Right? So the gain has sort of decreased by this amount, GMRE. Right? And input resistance, look at here, input resistance is increased by R pi plus RE GMRE, and output resistance R naught is still equal to RC, which is there here. All right, so this is there. We can add one more part to it, which is what happens when you look from here. Okay, so let's add that particular part, just so that you understand that well enough. Let me draw this again, the circuit here. So in this case it's slightly different. R pi GMV pi. Let's say for the moment let me put it to ground. Let me put it to ground. Let me put it to RE. Let me put it to RE. And now let's define, this is my signal Vs. Vs, and let's define this as V naught here. This is V naught. Okay, this is V naught. I'm taking the output here, and input is applied here. So in this case, what will be V0 by Vs equal to? Again, how will you do that? Remember how we transformed the resistor to the input side? So what will V0 by Vs equal to? Re will become, note that Re becomes 1 plus Gm R pi. Remember, this resistor, when you transform it, becomes like this, divided by R pi plus Re 1 plus Gm R pi. Right, so that becomes the gain of this, and obviously you can see the gain is less than 1. Input resistance is same. We've already calculated Rn. We know how to do that Rn. What about R0? Looking from here, what about R0? What did we calculate last time? That when you look, so when you look from here, R0 is, there's obviously Re parallel, so there is Re, and then what is the resistance looking from here? So we said whatever is the resistance here in this part, it becomes R pi, in this case is only R pi, gets divided by Gm R pi, same factor here. This Re was, when you look from here, was getting multiplied. In this case, when you look from here, this resistance gets divided by R pi by 1 plus Gm R pi. Okay, so that becomes your R naught at this particular stage. Okay, and note that depending on the values, the R0 can be fairly small. If I put in some numbers and all that, you can see, because it's getting divided by a large factor here. Okay, all right, so let me add then a circuit like this. Now let's do this. Here R pi GMV pi RC V naught. Let me put it to ground here, and let me add a resistor Re, and let me add a source here Vs. And what I'm looking for is what is V0 by Vs. What will be V0 by Vs? Yeah, please, others also, please try it out, do it. How many got GMRC? You all got GMRCs. Easy to see. When you apply Vs here, V pi is basically equal to minus Vs, and then this becomes GMV pi, so you're right. We get here GMRC. But note that there is no minus here. There is a plus. There is no minus here because V pi is equal to minus Vs. So the direction of the current reverses and it flows like this here through RC. So it's plus RC. Now Rn, can we say what will be Rn? Rn would be what? Looking from here, from the source side. Remember, that's the same thing that we had written earlier. Rn would be what was earlier, R0, right? Re parallel, same, R pi by 1 plus Gm R pi. R0, since we are talking about here, R0 will be equal to, basically equal to RC. Right? So we have this circuit looked at from various angles. This particular circuit has been looked at from various angles, whether I put the source here, whether I put the source here, I take the output here, I take the output here, all kinds of different combinations that we have done to see what is the impact here. All right, let's continue. Last lecture, we said that let's look at these two circuits here, R and C and V0, and let's apply Vs here. That's one circuit, and the other one is C and R. Simple circuits, but they're useful for us. C and R, Vs and V0 here, right? We said this circuit, if we plot V0 by Vs, V0 by Vs, this circuit, by the way, before we do that, let me, this thing here, suppose there is a circuit. There is a circuit here. Before we do that, there is V in and there is V0, right? And let's say we have gain AV equal to V0 by V in equal to 100, right? What is the gain in dB? Gain in dB. How do we do that? 20 log 10 AV, right? AV, which gives us 40 dB. What about gain of 50? How much is it in dB? Gain of 50 in dB? Huh? 30? How? 34? So is 50 would be, we can write it as 20 log 100 by 2, right? So this will give us 20 log 100 minus 20 log 2, right? 20 log 100 is 40. Log 2 is what? 0.3. 0.3. So this is basically 6, right? So you're right, 34 dBs. So what I wanted was everybody to know that log 2, remember, log 2 is 0.3, and okay. So here, in this case, what we are plotting is V0 by Vs, and we are plotting it in dBs. We are plotting it on a log scale, and we are plotting frequency here. Okay. So we know that this one, RC, will give us a behavior like this. Will give us behavior like this here. Okay. What would be the gain in dB here? If I'm plotting gain in dB, what will it be? So why don't you all calculate the transfer function there? V0 by Vs. What will it be? By taking, you know that C basically is, C you model it as 1 over J omega C, right? So why don't you just calculate the transfer function? Transfer function of this one will be 1 over J omega C by R plus 1 over J omega C H omega of this circuit, and if we do that, we get 1 over 1 plus j omega CR, and if we take mod of H omega magnitude, so we get 1 over square root 1 plus omega square c square r square, right? So at omega, if we're at very low frequencies, the gain is practically equal to 1, so this is equal to 0 dB. And at omega equal to omega CR equal to 1, we get 1 plus 1, 1 over root 2. So we get what? Yeah, but what is it in dB? At omega equal to omega CR equal to 1, you get 1 over root 2, but 20 log 1 over root 2 would be 3 dB, right? So this is now, this point is minus 3 dB. So that's why this frequency that we have, we call it minus 3 dB frequency. So F3 dB equal to 1 over 2 pi CR, right? That's the 3 dB frequency here. So it tells us, basically tells us when the region is flat and when the region begins to fall, right? So this is fine. Similarly, you can easily plot this fact. This one will go the opposite here. This goes like this versus frequency, and here also this part is 0 dB and 3 dB point, F3 dB, and F3 dB is again given by the same formula, 1 over 2 pi RC. So these two circuits are important. This one is for us, it shows us the low pass filter, LP filter, and this is our high pass filter. Okay, these are important for amplifiers. We'll see later on. Okay, so this is one background, but let's continue with this. Suppose I have a circuit like this. There is a circuit here, R1, R2, there is a C here, and there is an R3 here, V0 by Vs. Suppose we were to plot V0 by Vs. What will it look like? V0 by Vs. Again in dB. Mod in dB. What will it look like? How will it look? R1, R2, C, R3, all these resistors there, but one capacitor is there. How will it look like? Why?
Because the voltage Vs will be divided between R1 and R2.
Okay.
So R2.
Okay.
And then we can simply take it as the start, that node as R2 Vs by R1 plus R2.
Mhm.
So that will be the voltage.
Okay, before you're trying to calculate, right, the transfer function. But if you just look at the propagation of the signal, look at the propagation of the signal, Vs. Vs starts from here, travels here, right? Comes here, of course, comes here, something will get dropped here, then tries to go through this. Now, if frequency is low, what would capacitor tend to do? If frequency is very low, capacitor will just tend to block it. Right? Low frequency signals will get blocked by the capacitor because we know that reactance or impedance of a capacitor is 1 over j omega c. So very low frequency it will get dropped, nothing will reach V0. So at low frequencies it will get blocked. At very high frequencies we see omega c here. It will be almost like a short. And so we expect that the characteristics will go like this. You're right, a high pass filter. Now the issue is high pass filter. Can we calculate what will this value be? What will that maximum value be? That maximum value in dB will be 20 log 10 what? And then there would be a 3 dB frequency here. We'll go to this point and we'll say, let's say this is 3 dB here, and we want to calculate the F3 dB. This is 3 dB. Right, so what is this 20 log 10? Starting by, if the frequency is very high, so just use the limit. If the frequency is very high, what happens to the capacitor? Huh? If the frequency is very high, capacitor acts as a short, right? So what happens to R2 and R3? They're in parallel. So would it be not R2 parallel R3 divided by R1 plus R2 parallel R3, right? These two will be in parallel and they're in series, so it's a voltage divider. Okay, so that's this particular point here. What about F3 dB? How do I calculate F3 dB? How do I calculate that? How do we do that? Well, the procedure, whenever there is one single capacitor, you know that F3 dB is going to be equal to 1 over 2 pi C multiplied by some R effective. That's what 3 dB is going to be. So the issue is to find what is R effective. And so the way we find R effective is, let's go to that circuit. So we have this circuit here. We have a capacitor here and we have a circuit here, and we want to find out what is R effective. R1, R2, R3, and this is C. So R effective is nothing but the effective capacitor, effective resistance seen by C. Effective resistance seen by C. Okay, so R effective is what? Effective resistance seen by capacitance. Now how do we do that? What is the effective resistance seen by? So it brings us to the same thing. What is the resistance looking from a particular point? So what we do is, if you want to calculate this, remove this C here. Sorry. Remove this C here. And we are asking what is the effective resistance seen from here, right? Remove the C from here, and we are asking what is the resistance looking from here, right? sorry, what is the resistance looking from here? When I look between these two, what do I see? Effective resistance seen from here, which is the same thing as resistance seen by C here. C was here. So the resistance looking from between these two places here, that's my effective resistance. Now to calculate any effective resistance, what do? We said remove all independent sources. So we remove this. We remove this, we short it. What is the resistance seen between these two? Now we can see clearly, we don't have to do that, we can see clearly R1 is in parallel with R2 and there is R3, so effective resistance is R1 parallel R2 plus R3, right? If you have trouble, then in some cases it's very obvious when you are seeing it. If you have trouble doing this, all that you can do is, what you can do is, the method for calculating effective resistance is attach a source here. Source here plus minus, you can say Vx, and find out how much is the current flowing here, Ix. Solve this circuit. So Vx by Rx, Vx by Ix will give you R effective. If you have doubts as to if the circuit is complicated, just do Vx by Ix. Attach a source, take the ratio, and we'll give you that. So this gives us R effective equal to R1 parallel R2 plus R3. Okay? So any circuit which contains a single capacitor, you should be able to find this 3 dB frequency, because 3 dB frequency will always be, F3 dB will always be equal to 1 over 2 pi R effective multiplied by C. All that you have to do is find out what is that R effective. That's it. If there is one capacitor. If there are multiple capacitors, then it becomes an issue. Okay, so let's come back then to our circuit here. Let's come back to this circuit here. Remember this circuit here that we've been talking about? R pi, GM V pi, RC, V naught, V naught here. Now what we do is we add a capacitor here, we add a resistor RS here, and we add Vs here, and same V pi, and this, let's say this capacitor C1, let's call this CB. So what will our gain now look like? Can you see now what the behavior would be? How would V0 by Vs behave? When the capacitor was not there, we knew. When the capacitor was not there, we knew V0 by Vs was equal to minus GMRC, right? Now with the capacitor, what is going to happen? Now everything becomes a function of, the moment you put a capacitor, everything becomes a function of frequency. Now, when it becomes a function of frequency, there's only one capacitor. So what we would like to know is, how will this go? When I do V0 by Vs versus frequency, how is it going to go? High pass filter, everybody sees? Because at low frequency, what will the CB do? It will block Vs. Block Vs, which means that, note that at low frequency again, 1 over omega CB is going to be so high that your Vs is going to drop across the CB only. Nothing will appear here, V pi, because it's a voltage divider. Everything will drop across CB. Nothing will appear here, and nothing will appear at V0. At very high frequencies, what will happen to CB? Acts as a short. So our behavior is going to be like this. What is this value? V0 by Vs would be what? Its behavior is going to increase with frequency and then eventually saturate. this value will be equal to, I mean, if we take the magnitude, GMRC, because the capacitor is acting as a short here. In this region, the capacitor is acting as a short. Right? There is no effect of capacitor here. Why do we say there is no effect of capacitor? Because if there were an effect of capacitor, things would have been changing with frequency. The effect of capacitor is to make something frequency dependent. This is not varying with frequency here. There is no effect of capacitor. So what is happening? Frequency is so high that 1 over omega CB is not a short, but what happens is 1 over omega CB is actually much smaller than, let's say, R pi. Right? 1 over omega CB is actually much smaller than R pi, and therefore there is very little drop here. Now, what will be the 3 dB frequency for this? F3 dB. How much will it be? One capacitor, 1 over 2 pi CB multiplied by, well, R pi and RS. That's it. The resistance seen by this thing will be RS plus R pi. And that's it. You found out the 3 dB frequency of this. Now, if you want your amplifier, if let's say this is an amplifier, right? V0 by Vs, let's say for some design is giving you minus 100. Minus 100 means 20 dBs, right? 40 dBs. 40 dBs. So it's an amplifier with a gain of 40 dBs, right? But if I want to use it as an amplifier, and let's say if I do this calculation, it comes out to be 100 Hertz. What do I have to do? What do I have to do to operate it as an amplifier? Vs is here and V0 is here. To operate as an amplifier, I have to use its frequency above 100 Hertz. Then only it will act like an amplifier. Below 100 Hertz, why will it not act like an amplifier? No, so let's say the gain is 100 here. How much would be the gain here at this point? If the gain is 100 here, at 3 dB point, how much is the gain? 100 by root 2. So which means roughly 70, right? 1 over root 2. So the gain is 70 here. If somewhere here I'll get, the gain will be say 50. Somewhere here I'll get, the gain will be maybe 10. It's falling, right? It's falling, so 10 is 10. So still there is a gain, but why don't I want to operate my amplifier here? Fine, I mean, you're right, the gain is small. Gain is not 100. But can I operate here? Would I like to operate here? What will be the issue? See, somebody gives you an amplifier, is 3 dB cutoff frequency is 100 Hertz. Now for some application you want to amplify a signal which is not 100 Hertz but maybe 40 Hertz. Will you go and use this amplifier and amplify for 40 Hertz signal? What is the issue? What is the issue? It will give you less gain. Right? It will give you less gain, but it will still amplify. But normally what happens is, note that nobody is wanting to amplify a single frequency. You're not wanting to amplify ever a single frequency. Why would you want to amplify a sinusoid? You want to amplify your speech signal. You want to amplify music or whatever it is. Now in a speech or a music, what do you have? You have 1 kilohertz, you have 10 kilohertz, you have all these different frequencies that are there. And their amplitudes are in certain ratios. You know, high frequency may be high, low, and low frequency may be high, they're in certain ratios. Now if I pass this music signal and your amplifier, you operate it here, what would happen? Different frequencies will get amplified by different amounts. So you don't get that same signal here. The high frequency signal will see a more amplification, the low frequency signal will see a less amplification. So it will cause the distortion of the whole thing. So you don't want to operate in this region here. You want to operate in this flat region here, where whatever is the ratios of different frequencies in your input signal, the same ratios will come if you operate it here. Okay? Alright, so this is there, fine. Let me change that to, by the way, if I operate it here, let's say, if I operate it here at this point, where the gain is 50, if I measure V0 by Vs, will it be equal to minus 50? Will V0 by Vs be equal to minus 50? Do you realize what is the meaning of minus? When I say 180 degree phase shift, right? That between V0 and Vs there is 180 degree phase shift. Now if I operate it at this point here, will I still get 180 degree phase shift? So that gets back to the previous case here. Let's get back here. Let's get back here, right? In this case, what is V0 by Vs? So what is the phase shift here at this point? Look, this is the V0 by Vs, 1 over omega c, j omega cr. What is the phase shift that we here? Phase shift is equal to tan inverse omega cr, right? Phase shift is tan inverse omega cr, 1 plus j. Minus, minus, okay. So at omega equal to 0, what is the phase shift? 0. So there is no phase shift between V0 and Vs. And at 3 dB point, what is the phase shift? Omega cr equal to 1. So minus tan inverse 1 is 45 degree. So there is a 45 degree phase shift. If you go to very high frequencies, then even higher, pi by 2. So your phase is going from 0 to 45 to pi by 2. Right? So with that, if you go back here, the question that I asked, in this region, what do you think would be the phase? Obviously it will not be 180 degree. In this region the phase would be something else, less than 180 degree. Alright, so note that yes, when you go in this particular region, maybe you get a gain of 50, but you also get a phase shift, which is no longer 180 degree out of phase with the input. You get some other phase shift. Okay. All right. Let's continue with this. Let me draw another circuit for you. Let's stick with this here. Alright, what will V0 by Vs look like? In this case, how will it look like? Again, it will be a function of frequency. If we plot V0 by Vs as a function of frequency, how will it look? So will it be low pass or a high pass? High pass, you see clearly that this again acts as a blocking capacitor at low frequency, so again it will go like this. And our 3 dB point F3 dB will be equal to 1 over 2 pi, again Cc multiplied by R effective. So what is the R effective seen by here? RC plus, because we have to calculate what is the net resistance seen by C. So what is the resistance looking from here? Infinite. So it doesn't matter. So resistance seen by Cc is nothing but RC plus RL. This RC and this RL. Okay. All right. Let's look at this circuit then. Again, we are interested in V0 by Vs. We are interested in knowing how does it go with frequency. What will be the variation from V0 by Vs as a function of frequency? Again, look at the two extremes. Very low frequency, what happens? And very high frequency, what happens? Very low frequency capacitor is like open circuit, and very high frequency is like short circuit. So very low frequency, if it is open circuit, then V0 by Vs is what? Remember, V0 by Vs is what? In that case, omega tending towards 0, V0 by Vs will be equal to GMRC by 1 plus GMRE, right? Okay, fine. And omega tending towards infinity, V0 by Vs is minus GMRC. So if I look at the magnitude, what is happening? Right? At low frequencies it is this value, and at higher frequency it is this value here. Correct? So if I start with this value here, what would be the 3 dB frequency? Let's say if I take this value and go down here and look at 3 dB point here, so what will be 3 dB here? 3 dB would be what? F3 dB equal to 1 over
2 pi CE.
yeah, F3 dB equal to 1 over 2 pi CE, and the effective resistance seen by,
RE parallel R pi upon
which we did this earlier, is the output resistance looking from here. So you see those things are very important. Resistance looking from one place, resistance looking from the other. So we've already seen that. What is the resistance looking from here? And that will be equal to RE parallel R pi by 1 plus GM R pi. So that gives us the 3 dB point here. Okay. All right. With that, let me give you an example then. Here. With some actual values. One microfarad, 1 kilo ohm, 0.1 V pi. This is V pi. This is all capacitors are 1 microfarad. Let's put 1K. One K, 2K, 2K, 1 microfarad. We put 3 capacitors now at all these places. Do we see that all these capacitors, they have an effect of high pass? We've already seen this, this and this, right? Now how do we handle? I want to know an approximate value of F3 dB. Now the way to do this is follows. Assume that one of the capacitor is dominant. Okay, so start by assumption that one of the capacitor is dominant. You say, well, maybe this is the one which is causing this 3 dB. So when you assume that this capacitor is causing 3 dB, assume that this capacitor is short. This capacitor is short. Because note that what can happen. If you think about it, let's take this capacitance C1, let's take this capacitor C2, and let's take this capacitor C3. Now we've all seen that C1 has an effect of causing like this, right? But suppose C2 also, if let's say C1 were not there, suppose C2 were to cause an effect like this here. This is C2 and this is C1. Right? Note, see what I'm trying to say. Let's say C1 and C2. I suppose C2 was not there, and then C2 was not there, then C1 will cause like this. Now in the other case, C2 is there but C1 is not there, and so this is causing. Not there means the capacitor is it's not there in the circuit. In this case it's a short. Let's say in this case there's a also a short. Okay, so if this is the case here, C1, note, if this is the case here, what should I do to C2 in this case when both of them are present? Suppose I say that V0 by Vs. So what I'm saying is the following. Okay, let me write like this. What I'm saying is that this gain is there, and this gain is falling because of, let's say, C2. Gain is falling because of C2. It's not falling because of C1. C2 is dominant. Now in this region, both C1, C2, C3, they all act as, in this region where it is flat, all of them are acting as shorts. They're all acting as shorts. Now I'm saying I keep on reducing the frequency and C2 causes it to fall, which means C1 and C3 are still shorts, right? They're still acting as shorts. C2 is no longer short. On the other hand, if I say C1 is causing this to occur, then what do I mean? C2 and C3 are short and C1 is there. On the other hand, if I say C3 is causing it to fall, then I assume C2 and C1 are short and this is causing it to fall. So our method is as follows. What we assume is, let's say C1 is causing it to fall. Then what do? We assume the other capacitors are short. And so what you do is, for C1, corresponding to C1, you calculate a frequency F1. For C2, you calculate a frequency F2. Assuming all others are shorts. C2, C3 are shorts here. C1, C3 are shorts here. Then you calculate for C3, F3. Right? You will get 3 frequencies. Let's say this frequency is the highest. Okay, suppose I calculate and I find this is 1 kilohertz. This is 100 hertz. Suppose, and I say this is 200 hertz. What do you think is the 3 dB frequency? See, starting from here, right? And this is saying it will begin to cause it to fall at 1 kilohertz. Its effect will come much later, 100 hertz and much later. So approximate value of 3 dB frequency would be F2. Alright, so our procedure is calculate F1, calculate F2, calculate F3. If one of the frequencies turns out to be much higher than the other, that one would become the 3 dB cutoff frequency. If all of them are comparable, then things are complicated. Then best thing is to go and simulate and get some values there. All right, things are more complicated. It would be related to F1, F2, F3. You know, in some fashion, there are some expressions which are there. So what I want you to do is, in this case, find F1, find F2, find F3, and find out which one. What is the 3 dB cutoff frequency for this case here? 3 dB cutoff frequency for this amplifier. What is the value?
Around 8.12 kilohertz.
8.12 kilohertz.
Yes.
Okay, let's see. So the 3 dB frequency is decided by which capacitor?
C2.
C2. Okay, so let's do C2. So it will be equal to F2 1 over 2 pi C2 multiplied by the effective resistance seen by C2, right? Which will be equal to how much? 1K parallel 1K plus 1K divided by
1 plus
GMR pi. So it would be, if I were to look at, approximately equal to 2K divided by 100. Huh? 2K divided by 100. Yes or no? Because 2K divided by 100 gives me 20 ohms. 20 ohms in parallel with 1K I don't need to consider, right? So my frequency would be equal to, let me put an approximate sign, 1 over 2 pi 20 into 10 power minus 6 here. So that's equal to 10 to the power 6 divided by 40 pi, which is equal to 40 into 3 is 120. In kilo ohms, huh?
7.96.
Okay, fine. So now you know how to calculate the, if you have multiple capacitors, if one of them is dominant, then it's easy to calculate what is the 3 dB cutoff frequency here. Okay. Let me ask this question here now. Suppose we take a signal like this here. For the sake of this thing argument, let's say, let me just put 1 kilo ohm, 1 kilo ohm, 1 kilo ohm, 1 microfarad. Oh, this constantly goes 1 picofarad. V naught by Vs. How do you think V naught by Vs will go? Let's call this capacitor C1. Let's call this capacitor C2. Now, investigate the role of each capacitor. What does C1 do? What is the impact of C1? Impact of C1 means, look at low frequency when it acts as an open circuit and high frequency when it acts as a short. So what is C1 doing? What is C1 doing? Is it causing a high pass or a low pass? C1. High pass? Agreed? C1, everybody should see. C1 is causing a high pass behavior. High pass behavior. What about C2? C2 is causing a low pass behavior because at low frequency is open circuit and at high frequency it is short, so it's making V0. So this is causing a low pass behavior. Low pass behavior means is causing like this, and high pass behavior is causing like this. Now let's suppose we want to calculate the 3 dB frequency due to each one of them. So how do we do that? Suppose this is causing a low pass, right? So suppose let me draw like this here. Yeah. So in this region, in this region, note that this is flat. I'm drawing flat. Suppose I'm drawing like this, a characteristic like this. I'm drawing flat. What do you think is C2 behaving as? In this region, C2 is behaving as open circuit, and C1 is behaving as? C1 is behaving correct. So C2 is open and C1 as short. So are you seeing that there is a possibility that my graph looks like this? There is a possibility. We need to check that this capacitor is causing this behavior, high pass, and this is causing this. It may be acting like this. We need to check it. Okay, so if this is true, then C2 is open and C1 is short. In this region, C2 is it still open? In this region, not short, but C2 cannot be considered as open now. But what about C1? We are going to even higher frequency, so it can be considered as, so C1 will remain short and C2 will be now there. So how do I calculate the 3 dB cutoff frequency here? F3 dB. To calculate this 3 dB cutoff frequency, are you seeing that I can consider C1 to be short and calculate the effective resistance seen by C2? So what will that value be? 1 over 2 pi C2 multiplied by R2 effective, which will be equal to what? R2 effective would be what? 1K plus 1K, 2K in parallel with 1K. So 2K in parallel with 1K. So R2 effective would be 2K in parallel with 1K. And note the value that I have given here, 1 PF. So what is this frequency equal to? F3 dB, this F3 dB, this one here, sorry, let's write it there, will be equal to 1 over 2 pi 10 to the power minus 12 1 pico multiplied by 1 plus 2k, sorry, 2k parallel 1k, 2k parallel 1k. So this frequency is going to be this much, fairly high frequency, right? Several megahertz frequency here, several megahertz frequency. Alright, so we can calculate this frequency here at this point. What about this now? Let's look at this point here. So in this entire region, you all agree C2 is open and C1 is short. So now if I come here at this point, do you think C2 can still be considered open? If C2 is open here and I go to even lower frequency, C2 should still be open, but C1 is no longer short. So to calculate this frequency, what should I do to C2? C2 should be open circuited. To calculate this frequency, suppose I call it FL, and I call this as FH, higher cutoff frequency and lower cutoff frequency. So this is FH. So here C2 should be considered as open and C1 should be considered as there. So FL will be equal to how much? 1 over 2 pi C1 multiplied by what? Multiplied by 1K, 1K, 2K plus 1K, 3K. Right? And if you calculate the value, C1 is in microfarad. C1 is in microfarad. And this one was in picofarad. So you will see that it is correct, that FH is greater than FL. This value will be come out to be in several megahertz, tens of megahertz and all that. It will come out. This value will come out to be in less than a kilohertz. So there is a range here, which is the range where my amplifier has a constant response. Amplifier is not changing with frequency. It's changing with frequency here, it's changing with frequency here, but in this region it's not changing with frequency here. Right? And so that's why we call this obviously as the mid-band region. There's a mid-band region here. So most amplifiers will have a region in the middle. At lower frequencies you will find gain is varying with frequency. At higher frequencies gain is varying with frequency. In the middle you'll find that there's a region which is gain is independent of frequency. And that turns out to be the most important range. We want to know what is that range. We want to know what is FL and we want to know what is FH in an amplifier. Because that defines the range within which I can use my amplifier, between FL and FH. Okay? Alright. Let me draw this circuit for you. Now let's see whether we understand the role of this one. Do we know what this capacitor will do? We can remove this for the moment. Let's remove this. Do we know what this capacitor will do to our V0 by Vs? How will it go? Test again, low frequency, high frequency, what will it do? Low pass. So you all see that? You all see it's going to go like this. At low frequency it is open, at high frequency it's a short, and so we can calculate 3 dB. FH equal to would be equal to what? 1 over 2 pi 1 over 2 pi C pi multiplied by RS parallel output. The net resistance seen, because remove the source, RS becomes in parallel with R pi. Correct? So we see the role of this C pi here, a capacitance here. What does it do? It causes it to fall, give rise to a low pass kind of a behavior, and we can calculate what his effect is. Okay? Alright. Let's look at this one. Let me remove that effect. Alright, and now let me add a capacitor here. What does this do? What does it do? Low pass, high pass? Hmm? Which one? Hmm? Low pass? Everybody's agreeing low pass? What is the reason? Alright, say you're saying, okay, low pass. Low pass behavior like this. Okay, why? Why like this? Low frequencies. Very low frequencies. What happens to CMU? Open circuit. Open circuit, what do we get? V0 by Vs? Minus GMRC. Fine. That's okay. So let's say this is some large quantity, let's say minus 100 or so, right? It's an amplifier gain 100. So this is there. So that's low frequency. High frequencies, this is beginning to get short. Beginning to get short here. This capacitor is acting like a short between here and here. If it's acting like a short, what will it do? Note that this is Vs that you applied here. So the signal at this point would be what? Less than Vs or more than Vs? Signal here is Vs. So signal here would be more than Vs or less than Vs at this point. Okay, this is here. Will it be less than Vs or more than Vs? This is Vs here at this point. Then there is a resistor and there's something afterwards. Obviously the voltage here will be less than Vs. The voltage here is less than Vs. Here, less than Vs. Now we are saying, what is the capacitor doing to us? Capacitor is causing a short to occur here. Which means what? V0 is becoming equal to this point. V0 is getting shorted to this point. So V0 is becoming less than Vs. So what has happened to the gain? Drastically fallen. So you see that this is the at low frequency, then at high frequencies here. So it's a low pass behavior. Right? So this capacitor contributes to a low pass behavior. Now it contributes to a low pass behavior. Now to find out the 3 dB frequency here, F3 dB, 1 over 2 pi C mu, fine, multiplied by what? Multiplied by what?
RS parallel R pi
R.
plus RC parallel 1 by GM.
Okay, so it's not straightforward. It's not straightforward. So what we need to do is to do that. So what we need to do is what I would suggest is all of you to do this. So we have a circuit like this. RS, and we have circuit like this, R pi, and we had here GM V pi, this plus minus V pi, and we had here RC, and we were wanting to find out what is the effective capacitance seen between these two, effective capacitance seen by C mu. Since it's not straightforward, what we need to do is we need to connect a source here. Connect a source plus minus Vx. Find out the current flowing Ix here. And in the meantime, remove this source here, remove this source here, remove it here, put it to ground. So obviously RS will come in parallel with R pi, fine. But then there is this GMV pi here and there is RC also here. So find out what is this Vx by Ix here. What is this R effective? R mu, capacitance seen by this, find out this particular value by actually doing the circuit analysis. Now by doing whatever. Okay, I'll please do that as a homework problem. Okay, take that as a homework problem and calculate what is the ratio of Vx by Ix and calculate this value here. So this circuit that we've been doing all this, right? All this that we've been doing here, R pi, RS, GMV pi, we put here RC, we had even put here RL, here V0, we had put here maybe capacitor, RS here, we put here resistor RE, put here capacitor here, CE, we put here capacitors here also, C pi, put here capacitors also, C mu, all these things that we have done here, maybe CB here, CC here, right? We've been analyzing these circuits without capacitors, with capacitors. We've been analyzing taking voltage here or taking voltage here, right? In the process of this analysis, what we have done, you will see that we have done all this. Common emitter. We have done common emitter amplifier. Common emitter or common source that you will see in MOSFET. Common base, common gate, common collector or common drain. All these amplifiers that you build either through BJT or through MOS. In fact, we've done, through this example, we've done all of them. You're now in a position to calculate gain, input, output resistance, lower cutoff frequency, upper cutoff frequency, all of that for all these amplifier stages. Common emitter, common base, common collector, common source, common gate, common drain. All these amplifiers that you will see, they will all go back and give rise to an equivalent circuit like this. That's why we've been spending so much time on this equivalent circuit. That this circuit, if you understand very well, the resistance looking from one place, the resistance looking from another place, the 3 dB due to this capacitor or 3 dB due to this capacitor. Once you understand this, you understand all of these here. Common emitter, common base, common collector, common source, common gate, common drain. They all give rise to an equivalent circuit like this. Okay? All of them will have equivalent circuit like this. That's why the analysis of these equivalent circuits is so important. Analysis is so important. Because eventually whatever amplifier you build, you will put the model of a transistor And once you put the model of a transistor, it reduces to this. Whichever amplifier circuit. For example, you are all familiar, we'll come to that, you are all familiar with this amplifier circuit. Right? There's a circuit like this. You've seen this. Let's take this V0 by Vs. This is a common emitter amplifier, right? Common emitter amplifier, you may recall, is a circuit like this. And if we want to analyze the common emitter amplifier, all the properties of this common emitter amplifier, what I would be doing is taking this transistor and replacing the transistor by its model. Remember, we said to analyze any circuit, you need KCL, KVL, and you need the models. So to analyze this, I'll need a model of it. And if I'm doing a sinusoidal analysis of this, or a small signal analysis, we'll come to that, we'll need a model of this. And when we plug in this particular model, what do we get? We get circuits like this here. We get a circuit of this kind. And therefore, all that we have learned in the last two lectures in discussion, how to calculate input, output, gain, everything, all that will be valid. All that we have to do now, if you look at it, we have to know how does a transistor behave. What is the model of a transistor? Once we understand the model of a transistor, we just have to go and substitute. And then the rest becomes the standard circuit analysis. And you will be able to get, because gain is what? V0 by Vs is your gain. Input resistance is what? Resistance looking from here. Output resistance is what? Resistance looking from here. All this we have already done. Simple circuit analysis. So all that you require, Rn, R0, all of this, all that we need to do is we need to understand the model. We need to understand the transistor. Okay? And same, you can take this out here, you can take this out, you can take this out and you can put a transistor here. A MOSFET here. I can take this out, here, and you can put a resistor, put a resistor here, and put a transistor here. Put a transistor here. That will give you your common source amplifier. Just with the MOSFET, it will give you a common source. Instead of common emitter, you'll get common source. And note that we were taking output here, right? So this gives you common source. Suppose I take the output here at this place. I remove this capacitor and I take the output here. And I get a common collector or a common drain. And which is the same thing. If you go back and see, we have said, what if you take the output here? Right? So we have all the answers that we are looking for to do a common source, a common collector or a common drain. We also looked at a case, if you remember, we said if you go back and suppose I add a source here at this point. We said, what if I remove this? We also today looked at a case, what if I remove this and I add an input here? Vs here, right? We add an input here. And we don't take an output here, we take an output at this place here, right? This is nothing but will give us a common base amplifier, common base or common gate amplifier. So all these things that you know, the basic amplifier configurations, common emitter, common base, common collector, is now, we can easily calculate all the parameters of a common emitter amplifier. Similarly, common base, common collector, common source, common gate, common drain. All the basic amplifier stages, you are in a position to understand and calculate everything. not just the gain, input, output, upper cutoff frequency, lower cutoff frequency, all of that you can calculate of all these amplifier stages. You also know, for example, now, the thing is, if I don't bypass this RE or RC, right? All of those things if I don't bypass or bypass and things like that, you can all calculate all of that. So our next stress is on then the transistors. Our next is, what is it? The transistors here, to understand the transistors. And before you can understand the transistors, what you need to do is a little bit understand the diode. Right? So you have this, the diode that we are talking about is our PN junction diode, P and N here, right? Now, how do I look upon a diode? See, the diode is one can look at it in a very simple way also, and one can look at it in a, one can spend, an entire course also on looking at diodes. It can be quite complicated also. So this is a circuits course, right? This is a circuits course where you want to understand a diode from a circuits point of view. So from a circuits point of view, this diode whose symbol that you are all familiar with, how do you look upon a diode? Say, in the sense that suppose I make a circuit like this. Let's make a simple circuit like this here. All right, I want to analyze this particular circuit. How should I look upon it? What should I do with the diode? With the resistor, I knew it's a voltage divider. But now that I put a diode there, what do I do with the diode? How do I look upon a diode? What is the behavior of a diode? When you see a diode, what is its behavior?
It can act as a switch at the below cutoff frequency.
No.
It will act as open. And in ideal case, after the cutoff voltage, it can act as a short circuit.
Shorts and opens and all that are depends. Even for a capacitor, remember, a capacitor, it depends on the context. Capacitor could be short, could be open, it could be neither. Right? So capacitor could act, depending on the circuits and all that, could act as a short. You could replace it by a short, you could replace it by an open. So a diode is not a short, is not an open. Diode is something else. You may be able to replace it. You know that sometimes you do replace it by a short. Fine. Sometimes you replace it by an open circuit. Sometimes you also know, okay, so these are things that you are probably familiar with. Sometimes I can replace it by a short, right? This is what you're saying, okay? Sometimes I can replace it by an open. Sometimes I can replace it by a, remember this model? 0.7 volt. Sometimes I need to replace it by not just 0.7 volt, but a resistance also. Some resistance also. Sometimes I may need to, the diode that you see here, I may need to replace it by a simple resistor. Sometimes I may need to replace the diode by a resistor with a capacitor. R and a C. All kinds of things. So these are all what? See, 1, 2, 3, 4, 5, 6. These are all what? These are all models of diode. These are all models of diode. They're all models of diode. Sometimes this may be okay to use it. Sometimes this may be okay to use it. Sometimes this may be okay to use it. Sometimes here, sometimes here. Right? Each model that you see here. So remember, what is a model? Model is not the real thing. Please keep that in mind. This model that you have, model, it's important to remember this phrase. What do I mean by model? It's a representation for a purpose. What is a model? Model is a representation. Model is a representation for a purpose. What kind of representation? Let me just add. It's a mathematical representation that we are looking at. A mathematical representation. A diode is there, is an entity, PN junction, all that is a physical entity. What we are looking for is a mathematical representation of that entity. And this is very important for a purpose. The purpose decides what kind of model am I going to use. The purpose, depending on my purpose, depending on the circuit, the short or an open circuit could be okay. Depending on the circuit, this short and an open may not be okay. This model may be okay. 0.7 volt model may be okay. Okay. So to understand my diode, the first thing that we need to understand a diode is the following. If I have a diode, the first thing that I need to understand is that if I apply, consider the diode under DC condition. Under DC condition, no time varying. DC voltage, DC current, right? If I look at my diode under this, so this is the voltage here, say plus here, minus here, let's call this voltage VD, and the current flowing through the diode is ID. So my diode is ID equal to IS e to the power VD by NVT minus 1. It can be more complicated than this. Remember, this is also a model. I'm building a model. This is also a model. There can be more complicated model also. But for us, this could be a starting point. A diode is like this, represented by this exponential characteristics. This, what is this called? It has a name. It's called reverse saturation current. Because now reverse saturation current. Note that this is so reverse saturation current here. ID, of course, is the volt. This VT is what? Thermal voltage. We call it the thermal voltage. Is equal to K Boltzmann constant KBT by Q, which has a value of around 26 millivolt at T equal to 300 Kelvin. Okay, which has a value of T equal to 300 Kelvin. This factor is called ideality factor, N, ideality factor. Well, under ideal case we take N equal to 1, but for many of the silicon diodes you may find N is maybe N equal to 2 also. So roughly between 1 and 2 is where N may lie, ideality factor. Now, as I said, this is not a complicated model. This is actually a simple model of a diode. There can be more complicated models. Okay. Now, if I were to plot this equation, how would this equation look like? If I were to plot it, how will it look? If I were to plot IV, looks like, right? And the current here, because this, note that the scale is very, 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 this thing, it would almost appear, there is a current, right? There's a current here, which is basically how much? IS. Because if you put VD equal to minus, you find that exponential will go to negligible value, and the current here is IS. So the I versus V looks like this here. This is exponential. right? It's an exponential curve. The other thing to understand about a diode is that this equation is not valid forever. If I keep on applying the reverse here, right? Eventually a stage comes where the diode starts conducting. The diode starts conducting even in the reverse direction, and we say breakdown has occurred, right? So this is the breakdown voltage, V breakdown. So to be on the safe side, you should stay away from the breakdown voltage. You should stay in this particular region, not go into that particular case. Forward bias, of course, it goes like this. Okay. Now, even in the forward bias, it doesn't remain exponential. If you go to very high forward bias, the current ID versus VD tends to become linear. So there are limitations. It doesn't continue to go and keep on increasing exponentially. It may start to become linear. Okay. So this is the behavior of the diode. That's how a diode under DC condition behaves. Okay. So if you go and let's say pick up a diode, whichever diode, let's say 1N4001, you will have a value of IS. You will know the value of N. And therefore, so in this, remember we said a model is a mathematical representation for a purpose. So in the model, there are always parameters. There are always parameters of a model. There are always parameters. This is an equation. This equation, let's say, is valid for all diodes. But different diodes will differ in what? Differ in the value of IS. Different diodes will have different IS. Different diodes may have different N. Different diodes may have different breakdown voltages. You know, you go and, for example, there are so many diodes available, and you can read the data sheet of the diode, and you'll find different diodes will have different IS, different N, different breakdown. They have these different characteristics. So these are the parameters of the model. The equation is the same, but different diodes will have different. Germanium diodes will have different value of IS. Gallium arsenide diodes will have different value of IS. Diodes with heavy doping will have lower breakdown voltage. Diodes with lighter doping will have higher breakdown voltage. So you can find diodes which have a breakdown voltage of 1000 volts, and you can find diodes which have a breakdown voltage of only 20 volts. And so they will all have this equation, but they will have these different parameters here, IS, N, and BV. So now the thing is, so this is the your model. So now, what is the time now? Okay, so we'll stop at this. So let's say now that you know the model here, IS I equal to IS e to the power VD by N VT minus 1. All of you do the following. Suppose I take IS equal to 10 to the power minus 12 amperes. Right? IS equal to 10 power. For ID equal to 1 milliampere, and let's say N equal to 1. How much VD do I require? How much how much voltage do I have to apply across the diode to get a current of 1 milliampere? Say IS is 10 power minus 12 for my diode. It would be what? It would be straightforward. VT into ln 1 plus ID by IS, right? That would be this. What value does it give me? VT is what? How much? 26 millivolt into ln. 1 I can neglect. ID is 10 power minus 3, so this becomes ID is 10 power minus 3, and this is 10 power minus 12. So this is 26 millivolt into ln 10 to the power 9. How much is this? Somebody calculate? Calculator, anybody has a calculator? Yeah. Point? 0.53. 0.53 volt. So this says that I need to apply 0.53 volt to cause 1 milliampere current to flow. Correct? Okay. On the other hand, if let's say I change IS to 10 per minus 15, what do you think will be the diode voltage required? Same calculation repeated. So this will be 10 per minus 15, 10 to the power. VD would be 26 millivolt. ln 10 per minus 3 by 10 per minus 15 comes out to be 0.7. Okay, 0.7 volt. All right. So now let's make a circuit like that. I mean, so 0.7 volt. So do you see that depending on the nature of the diode, I'll have different voltages for the same current, 1 milliampere current flowing. In one case, if IS is 10 power minus 12, the voltage across the diode is 0.53. In another case, if IS is 10 power minus 15, the voltage across is 0.7. In some other case, if I make IS even smaller, I make it even 0.75. Right? So it all depends on what is the value of IS. For the same current, I will require different voltages too. Different voltages will be there here, right? So IS is very important. IS determines and N. So IS will determine how much voltage gets dropped across the diode here. So remember, diode is not a short. I'm giving you with this example that when you pass 1 milliampere current through the diode, they will be either 0.53 or 0.7 or somewhere around that particular value, maybe 0.6, depending on the value of IS. The diode will have certain voltage across it. Okay. So now the issue is this. Say I have a circuit like this here. How do I solve it? Now you know the model. The diode model is what? I equal to ID equal to IS, e to the power VD by, let's take ideality factor equal to 1, VD by VT minus 1. So you know the diode model. You know the resistor model, I equal to V by R. And you have this. So I would like to know what is the current flowing. How much is the current flowing here? How much is the current flowing? You have all the information. Remember how is analysis done? KCL, KVL, and the models. You have everything now. Let's say IS is, let's take IS equal to 10 to the power minus 15 amperes here. So this value is there. VT is 26 millivolts. So you have all the information available to you. I want to know what is the current flowing in this circuit. I've given you the model. Okay. Let's stop here. Try to do this particular problem. We'll continue from here. Okay.